Lesson 6.2 is titled Right Triangle Trigonometry. The content in this lesson will probably seem familiar to you from content you've seen before about trigonometry. Notice the right triangle down below. We know it's a right triangle because there's a right angle in the corner. That's formed by two perpendicular sides or legs of the triangle. Now some of you might remember the formula a squared, plus b squared equals c squared. And that would be the Pythagorean theorem. We'll use Pythagorean theorem to solve for certain side lengths when we need to, but Pythagorean theorem is just one of many ways we can compare sides and angles in a right triangle. In order to help us kind of interpret different side length connections, we need an angle that we start with. So if you look over here on that bottom left, there's an angle that looks like a capital O with a slash through it. When you see that symbol, that's known as theta. And we use that as our reference angle. And what we mean by that is the angle that we compare specific sides by. And you'll see that marked on the triangle. So notice where that theta is. If you go directly across from that angle, it says it's the side opposite theta. And if you go next to the right angle, that's the side that's adjacent to theta. Now, any side length that's across the right angle always defaults to the hypotenuse. So we have an adjacent side, which we abbreviate to make things easier to write out. We have the opposite side, which we again abbreviate. Put a parenthesis on there, I guess. And then we have the hypotenuse. Now those three side lengths will be useful with some trigonometric definitions down below. If you're writing these notes on your notebook paper versus having a packet, you don't have to write out this entire table. What I'd like you to for sure have on your paper is the right triangle definitions of trig functions, and then have these 6 definitions. You really wouldn't need anything else from that table. So notice the first one, it says sine theta equals opposite over hypotenuse. So sine is the trig term. Opposite and hypotenuse would be the fraction comparison of the two side lengths. COS is known as cosine. TAN is known as tangent. So sine is actually SINE. COS is cosine, and tan is tangent. And we just abbreviate them to make things simple. Notice all 3 of them compare 2 different side lengths on that right triangle. So sine compares opposite and hypotenuse, cosine compares adjacent and hypotenuse, tangent compares opposite and adjacent. You may remember this little mnemonic device called SOHCAHTOA. SOHCAHTOA. SOHCAHTOA is just a phrase to help you remember those definitions without having to write them out every time. Here's how they work. SOH, S stands for the trig definition. That would be sine. O divided by H would be the fraction, opposite over hypotenuse. C is cosine, and that stands for adjacent over hypotenuse. T is tangent, and that stands for opposite over adjacent. So you have sine, cosine, and tangent. SOHCAHTOA is just a way to kind of remember those without having to write them out every time. All right, but then there are 3 more, and we don't always hear about these 3. Notice for the first one that's right below sine, it goes by CSC. So we really can't even say that. CSC. CSC means cosecant. CSC is cosecant. Notice it says hyp over op, so hypotenuse over opposite. It's just the reciprocal of sine. So sine and cosecant are reciprocals of each other. Then you have SEC, and SEC is just secant. And again, you'll notice that it's type over ADJ, so that's just the reciprocal of cosine. How many of you think you can tell me what COT stands for? Not just cot, it's cotangent. And cotangent, as you can see by that fraction definition, is simply the reciprocal, oops, and I just highlighted it. Let's get rid of that little arrow there. It's just the reciprocal of tangent. So the abbreviations on the left are going to be what you want to remember. But we say them like the words on the right. Sine, cosine, tangent, cosecant, secant, and cotangent. Let's go ahead and put those definitions to the test. In our first example, it says if sine of theta equals 4/5, determine the other 5 trigonometric functions of theta. Oof, that's a lot to unpack. Let's first start by figuring out what this very first statement means. If sine theta equals 4/5. Well, we know the definition for sine. It's opposite over hypotenuse. That means we're going to need a right triangle on our paper. So let's go ahead and draw one. You can draw in any direction you want. Just identify the right angle and identify theta. So theta can be at the bottom or the top. It just can't be where the right angle is. I'm going to put it in the same spot it was in our picture. So I'm going to mark theta right here. Now, if the sine ratio is 4/5, what that tells us is that the opposite side length is 4 and the hypotenuse has a length of 5. So that's what we know from that very first part. We can draw a right triangle and label our side lengths. But it then says determine the other 5 trigonometric functions. The only one we really know right now, we could do cosecant because that's the reciprocal. But to get the rest of them, we're going to need that missing side length. And guess what? That's where Pythagorean theorem comes in. So if we think about a squared plus b squared equals c squared, Pythagorean theorem, the a and the b are the two sides, and you can put them in either order. C is always the hypotenuse. Hopefully you remembered that. So I'm going to label that bottom. I'm just going to pick a variable and I'm going to call it a. It could either be a or b. It doesn't matter. So if we're trying to solve for a, that means b will equal 4. And I have to square that. The hypotenuse is 5, so we're going to square that as well. Leaving a squared alone, 4 squared is 16, and 5 squared is 25. If we move 16 over by subtracting, we would get, that's an arrow, we'd get a squared is equal to 9. Take the square root of each side. Now technically a could be plus or minus 3 because it could be positive or negative. However, a side length is never negative. So for this case, we'll keep it as a positive 3 value. And now that we know a equals 3, we can find the rest of our trig definitions. I'm going to go ahead and list them out. We know we want cosine. We know we want tangent. And then we want those reciprocals. We want cosecant, which I guess we already could have gotten. We want secant. And then we're going to define cotangent. Cosine, by definition, is adjacent over hypotenuse. That would be, or hypotenuse, that would be 3/5. Tangent is opposite over adjacent for side lengths, and that would be 4/3. Cosecant is the reciprocal of sine. That's going to be 5/4. Secant is the reciprocal of cosine, 5/3. And cotangent is the reciprocal of tangent, so 3/4. Now eventually this information will help us determine what the measure of theta actually is. Let's try another example on the right. If secant theta equals 6, determine the other 5 trigonometric functions of theta. So 6, that's just kind of a random whole number. Let's see what we can do with that. Secant theta equals 6, but I'm going to write it as a fraction. I'm going to write it as 6/1 because that equals 6. If you remember secant's definition, that would be hypotenuse over adjacent. To create that, we're going to need that right triangle rule again. So let's go ahead and draw another right triangle on our paper. And again, you can draw it however you want, but make sure you show where that right angle is. I'm going to clean that up a little. There we go. And I'm just going to pick my right angle down here in the corner again, my theta. So hypotenuse has to be the side length opposite the right angle. And adjacent is the side length that connects the angle, or the theta, excuse me, to the right angle. So that has to be the adjacent side. So we could get cosine just by taking the reciprocal, but we need that opposite side length to get the rest of the trig definitions. So we're going to default to that Pythagorean theorem again. This time I'm going to let that vertical side length equal b. So this is going to be 1 squared plus b squared equals 6 squared. Now this doesn't work out quite as user-friendly as the last one did. 1 plus b squared is equal to 36. And if we move 1 over, we get b squared equals 35. So when you take the square root of 35, it's not a perfect square like we had last time. Well, here's the deal, everybody. We have to leave this in exact form. We're not going to do a decimal approximation. So that means we're going to have a square root in our answer, which totally involves some new things for us. All right, once we know all three sides, let's go ahead and list the rest of our trig definitions. I'm just going to go in order: sine theta, cosine theta, tangent theta. All right, let's start there. Sine is opposite over hypotenuse. So that would be square root 35 over 6. Cosine is the reciprocal of secant, adjacent over hypotenuse, 1 over 6. Tangent would be opposite over adjacent, which is square root 35 over 1, or just square root 35. So those weren't too bad. We already know secant, but we still need cosecant and cotangent. Cosecant is the reciprocal of sine, so that's hypotenuse over opposite. That is 6 over the square root of 35. Here's where we run into an issue. To have a simplified fraction, we can't have 35 in the denominator, so you need to rationalize it. This is happening. To rationalize the denominator, you're just going to multiply the top and bottom by whatever that square root is. And that would give us 6 times the square root of 35, since it's an outside and an inside. But on the bottom, if you take the square root of 35 times itself, the square root cancels out and it equals 35. Believe it or not, that is the simplified version of the square root fraction that we started off with originally. Okay, cotangent. Cotangent is the reciprocal of tangent, so that's going to be 1 over square root 35. And again, we've got to rationalize that. We'll multiply top and bottom by square root 35 over square root 35. In the numerator, 1 times the square root of 35 doesn't change, but in the denominator, the square root of 35 times itself just equals 35. Some of these problems will require work like this, and some of the problems will have perfect squares, and you'll end up with just kind of integer fractions or integers in your fraction answers. The last big thing that we're going to talk about in this lesson are the two special right triangles drawn down below. It says frequent angle measures on our circle that we were drawing yesterday, or in 6.1, include multiples of 30 degrees or pi over 6 radians. We also frequently use 45 degrees, and that could be pi over 4 radians. And there's also multiples of 60 degrees, which is pi over 3 radians. Now 30, 45, and 60 degrees come from these two special right triangles down below. Over on the left, we have what's known as a 45, 45, 90 triangle. On the right, we have a 30, 60, 90 triangle. Those should all be degrees right there. Sorry about that. We'll get those in there. And notice how the side lengths and angles compare. In a 45-45-90 triangle, since there are two equal angles, there are two equal side lengths. They're each equal to 1. And if you did Pythagorean theorem, you would get the hypotenuse to have a length of the square root of 2. In that 30-60 triangle, notice the bottom side is half of the hypotenuse. That vertical side length would be square root 3 if we did Pythagorean theorem. And I think this is actually going to put us at a really good stopping point. So tomorrow what we'll do is we'll complete this table of special angles, and then we'll finish with cofunction identities.